You have never touched anything in your entire life. Not the screen you are looking at right now. Not your coffee cup this morning. Not the hand of someone you love. Your atoms and their atoms have never made contact. The electrons in your fingertips and the electrons in everything you have ever touched repel each other with electromagnetic force, hovering apart by a distance too small to see, too real to ignore. You have spent your entire existence floating through the world, separated from everything by an unbridgeable quantum gap. But that is not the dark part. The dark part is what happens when you try to look closer. In 1901, a British scholar named Thomas Young shined a beam of light through two parallel slits in a screen. On the wall behind, he expected to see two bright bands, simple shadows of the slits themselves. Instead, he saw something that should have been impossible. A series of alternating bright and dark stripes stretching across the wall like the rungs of a ladder. This was an interference pattern. The kind of pattern you see when two waves crash into each other in a pond. The bright bands appeared where wave crests met wave crests, amplifying each other. The dark bands appeared where crests met troughs, cancelling each other out. Young had proven that light was a wave. Mystery solved. Except it was not solved at all. It was the beginning of a nightmare that physics has never woken up from. Because more than a century later, physicists repeated Young's experiment. But this time, they did not shine a continuous beam of light through the slits. They fired individual particles of light, photons, one at a time, single, discrete bullets of light shot through the apparatus like pellets from a gun. If light behaves as particles, the logic is simple. Each photon should pass through one slit or the other, and eventually, two clumps of impacts should appear on the detector screen behind the slits. Two bands. Simple. But that is not what happened. Even when fired one at a time, with gaps between them long enough that no two photons could possibly interact, the interference pattern still appeared. The bright and dark bands built up slowly, photon by photon, as if each individual particle was somehow interfering with itself, as if each photon was passing through both slits simultaneously. Richard Feynman, the Nobel laureate, who helped build the atomic bomb and reinvent quantum electrodynamics, called this result the only mystery of quantum mechanics. He said in 1964, in his famous Messenger lectures at Cornell, "I think I can safely say that nobody understands quantum mechanics." He meant it literally. Not that the math was hard. The math was fine. The math predicted the experimental results with breathtaking accuracy. What nobody understood, what nobody still understands, is what the math actually means. Because the math says something deeply uncomfortable about reality. It says that before you look at a photon, the photon does not have a definite path. It does not exist in one place or another. It exists as a wave of probability, a mathematical ghost that haunts both slits at once, interfering with itself in ways we can describe but cannot comprehend. And then you look, and everything changes. Here is where it gets uncomfortable. In 1927, physicists began to ask an obvious question. If each photon passes through both slits at the same time, why do we not simply observe which slit it goes through? Put a detector at one slit. Watch it. See what actually happens. So they tried it. They set up detectors to determine which slit each photon passed through. And the moment they did, the interference pattern vanished. Instead of the ladder of bright and dark bands, they saw exactly what classical physics predicted: two simple clumps directly behind the two slits. The photons, when observed, behaved like particles. The photons, when unobserved, behaved like waves. Let that sink in. The act of observation, of trying to know which path the photon took, fundamentally changed what the photon did. Not how we perceived what the photon did, what the photon actually did. This is the observer effect, and its implications are far stranger than any science fiction you have ever read. The standard explanation for what is happening here is called the Copenhagen interpretation. It was developed in the 1920s, primarily by Niels Bohr and Werner Heisenberg at the Institute for Theoretical Physics in Copenhagen, Denmark. According to the Copenhagen interpretation, quantum objects like photons and electrons do not have definite properties until they are measured. Before measurement, they exist in a superposition of all possible states, passing through both slits, spinning both up and down, existing in multiple places at once. The wave function, the mathematical description of this superposition, contains all the probabilities for every possible outcome. Then, upon measurement, the wave function collapses. The quantum object snaps into a single, definite state. The probability becomes certainty. The ghost becomes real. Bohr insisted that this collapse was not a problem to be solved, but a fundamental feature of nature. We cannot ask what the photon was really doing before we measured it, he argued, because before measurement, there was no really. The question itself was meaningless. The properties we observe are not discovered, but created by the act of observation. Heisenberg put it even more starkly. In a world without observation, he said, quantum mechanics describes not what is, but what tends to be. But what does observation actually mean? This is where the darkness begins to creep in. In the double-slit experiment, the photon passes through both slits when unobserved, and only one slit when observed. But the detector is not alive. It is not conscious. It is just a piece of equipment. So, what counts as an observation? Bohr said it was the interaction with a macroscopic, classical measuring device that caused the collapse. The boundary between the quantum world and the classical world, wherever that boundary was, marked the point at which probabilities became facts. But this answer immediately raised another question. Where is that boundary? Consider what happens when a photon hits a detector. The photon interacts with atoms in the detector. Those atoms become entangled with the photon state. If we are being consistent, the quantum description should now include both the photon and the atoms of the detector, all existing together in a superposition of possible states. When does the collapse happen? When the atoms in the detector register the photon, when the signal travels through the electronics, when the data appears on a screen, when the scientist looks at the screen. In 1932, the mathematician John von Neumann analyzed this problem rigorously in his book Mathematical Foundations of Quantum Mechanics. He showed that the mathematics of quantum mechanics allows the collapse of the wave function to be placed at any point in the causal chain, from the measuring device all the way up to the subjective perception of the human observer. Von Neumann left the question open. He showed that quantum mechanics worked equally well whether you place the collapse early or late in the chain of observation. But he did not say which was correct. And this opened a door that many physicists wish had stayed closed. Eugene Wigner was a Hungarian-American physicist who won the Nobel Prize for his work on nuclear physics. In 1961, he published an article called Remarks on the Mind-Body Question that pushed von Neumann's analysis to its logical extreme. Wigner proposed the collapse of the wave function could not happen without consciousness. He formulated his argument using a now famous thought experiment called Wigner's friend. Imagine Wigner has a friend who performs a quantum measurement in a sealed laboratory. From the friend's perspective, the measurement is complete. The wave function has collapsed, and a definite result has been obtained. But from Wigner's perspective, outside the laboratory, quantum mechanics suggests that both the friend and the measurement apparatus should exist in a superposition of states until Wigner himself observes the result. The friend should be simultaneously experiencing having seen outcome A and having seen outcome B. Wigner found this absurd. He argued that consciousness must be the demarcation line that triggers collapse. The moment a conscious mind perceives a result, the superposition ends. This interpretation has fallen out of favor. Most physicists today reject the idea that consciousness plays a special role in quantum mechanics. Wigner himself backed away from this position in the 1970s and 80s. In a 1982 lecture, he acknowledged that his earlier views could be criticized as a form of solipsism. But the question Wigner raised has never been fully answered. What makes a measurement a measurement? What is the physical difference between a quantum system that remains in superposition and one that collapses? If consciousness is not the answer, what is? And perhaps more disturbingly, if we cannot answer this question, how do we know what quantum mechanics is actually telling us about reality? In 1935, the same year that Albert Einstein, Boris Podolsky, and Nathan Rosen published their famous challenge to quantum mechanics, another physicist took a different approach to exposing what he saw as the absurdity of the Copenhagen interpretation. Erwin Schrödinger, one of the founders of quantum mechanics and the creator of the wave equation that bears his name, proposed a thought experiment so vivid, so disturbing, that it has haunted physics ever since. Imagine a cat sealed in a box. Inside the box is a vial of poison, a hammer, a Geiger counter, and a small amount of radioactive material. The radioactive material has a 50% chance of decaying within 1 hour. If it decays, the Geiger counter detects the radiation, triggers the hammer, and smashes the vial, killing the cat. According to quantum mechanics, until we observe whether the radioactive material has decayed, it exists in a superposition of decayed and not decayed states. The Geiger counter is therefore in a superposition of triggered and not triggered. The hammer is in a superposition of fallen and not fallen. The vial is in a superposition of broken and intact. And the cat, by this logic, is in a superposition of alive and dead. Schrödinger designed this thought experiment as a reductio ad absurdum, a way of showing that the Copenhagen interpretation, taken to its logical conclusion, produces ridiculous results. Cats are not alive and dead at the same time. Therefore, something must be wrong with the interpretation. But here is the problem. Quantum mechanics, as it stands, gives no clear answer for when or how the superposition ends. The mathematics simply does not say, and so, for nearly a century, physicists have been left with a choice. Either accept that cats, and by extension, everything, can exist in superpositions of contradictory states until observed, or modify the theory in some way to explain why large objects, like cats, do not exhibit quantum weirdness. Neither option is comfortable. There is another response to Schrödinger's cat, one that seems to solve the problem, but carries its own unsettling implications. In 1957, a graduate student at Princeton named Hugh Everett III was thinking about the foundations of quantum mechanics. His advisor was John Archibald Wheeler, who had worked with Niels Bohr and would later coin the terms black hole and wormhole. Everett asked a simple question. What if the wave function never collapses? In the standard Copenhagen interpretation, measurement causes the wave function to collapse from many possibilities to one actuality. Everett proposed instead that the wave function always obeys the Schrödinger equation. It never collapses. It simply keeps evolving, forever. But if that is true, what happens when a measurement is made? Everett's answer was radical. When a quantum system interacts with an observer, both the system and the observer become entangled. The combined wave function now contains branches, one for each possible outcome of the measurement. In each branch, the observer sees a definite result, but all branches exist simultaneously. In other words, when you measure a photon's path through the double slit, you do not cause the photon to choose one slit or the other. Instead, the universe splits. In one branch, the photon went through the left slit, and you observed that. In another branch, the photon went through the right slit, and a different version of you observed that. Both outcomes happen. Both versions of you are real. Neither has more claim to existence than the other. This became known as the many worlds interpretation. Bryce DeWitt, an American physicist who popularized Everett's ideas in the 1970s, gave it that name because it implies the existence of a vast number of parallel universes, one for every quantum possibility, branching and multiplying at every moment. When DeWitt first encountered Everett's thesis, he wrote to the young physicist, complaining that the idea of the universe constantly splitting seemed absurd. We never experienced such things. Everett's response was pointed. I can't resist asking, do you feel the motion of the earth? DeWitt was won over. The fact that we do not experience something does not mean it is not happening. The many worlds interpretation solves the measurement problem in a certain sense. It eliminates the need for wave function collapse entirely. There is no mysterious moment when quantum possibilities become classical facts. Everything is always quantum. Every possibility is realized somewhere, but it carries a price. That price is an infinity of worlds we can never access. Every time a quantum event occurs, which is constantly everywhere, the universe branches. The number of parallel worlds is not merely large, it is incomprehensibly, unimaginably vast, and you branch with it. Right now, as quantum fluctuations occur in your body, in every atom, in every electron, versions of you are being created. Versions where a slightly different thought occurs to you. Versions where a neuron fires differently, where a choice is made differently, where you stop reading this and close the window. If many worlds is correct, all those versions exist. They are as real as you are. They just cannot interact with you anymore. You are continuously dying in branches you will never know about. You are continuously being born in branches you will never meet. Every moment, you are splitting into uncountable copies, each one convinced it is the original. This is not mysticism. This is what the mathematics of quantum mechanics predicts. If we take it seriously and refuse to add the special unexplained collapse postulate, and many physicists do take it seriously, the many worlds interpretation has gained substantial ground since Everett's time. A survey of physicists at a quantum mechanics conference in Austria in 2011 found that about 18% supported many worlds, roughly tied with Copenhagen as one of the most popular interpretations. Sean Carroll, a physicist at Caltech and one of the most prominent advocates for many worlds, puts it this way: the interpretation requires us to accept an enormous ontology, countless parallel worlds, but it has the simplest dynamics. No collapse, no special role for measurement, just the Schrödinger equation, all the way down. Whether that trade-off is worth it depends on what you find more disturbing: a universe where observation plays a magical, unexplained role, or a universe where everything that can happen does happen. Somewhere, forever, there is a third option, one that takes the measurement problem in an entirely different direction. What if the wave function does collapse, but not because of observation? What if collapse is a physical process, something that happens to quantum systems when they get large enough or complex enough, even when no one is watching? This is the idea behind objective collapse theories. The most famous of these is the Girardi-Rimini-Weber theory, or GRW theory, proposed in 1986. GRW theory adds a small modification to the Schrödinger equation. In this modified theory, wave functions have a tiny random chance of spontaneously collapsing at any moment. For a single particle, this chance is vanishingly small, roughly once every 100 million years. But for a large system like a cat, composed of roughly 10 to the 27th atoms, the probability that at least one component will collapse is essentially certain on timescales far shorter than a second, because all the components of a macroscopic system are entangled together. The collapse of any one part triggers the collapse of the whole. The cat's wave function collapses long before anyone opens the box. The superposition of alive and dead never persists for any appreciable time. This is elegant. It explains why quantum effects are invisible at everyday scales without invoking observation or consciousness. The transition from quantum to classical is a physical process built into the dynamics of the theory itself. But GRW theory makes different predictions from standard quantum mechanics. Predictions that, in principle, could be tested. Experiments are ongoing to search for signs of spontaneous collapse. So far, none have been found. The simplest versions of GRW theory have been ruled out by experiments with increasingly large quantum superpositions. Still, the basic idea that collapse is objective and physical remains appealing to many physicists. Roger Penrose, the Nobel laureate known for his work on black holes and cosmology, has proposed that collapse is triggered by gravity. In his model, superpositions of different mass distributions create superpositions of different space-time geometries, and the inherent instability of superposed spacetimes causes collapse. These ideas remain speculative, but they point to a possibility that many find more palatable than either Copenhagen or many worlds, that the universe has a built-in mechanism for transitioning from quantum to classical, and that mechanism has nothing to do with observers at all. In the 1980s, a physicist named Wojciech Zurek at Los Alamos National Laboratory developed a different approach to the measurement problem. It does not require consciousness, does not require collapse, and does not require parallel universes. It is called decoherence. The key insight is simple. Quantum systems are never truly isolated. Every quantum object is constantly interacting with its environment, air molecules, stray photons, the microscopic vibrations of whatever container holds it. Each of these interactions causes the quantum system to become entangled with its environment, and this entanglement has a devastating effect on superposition. Imagine a photon in a superposition of having gone through the left slit and having gone through the right slit. If this photon interacts with even a single air molecule, the air molecule becomes entangled with the photon's path. The superposition is still there, technically, but it now involves both the photon and the air molecule. As more interactions occur, the entanglement spreads. Soon, the superposition involves billions of particles in the environment, all entangled together in a fantastically complex web. From the perspective of an observer who only has access to the photon, not to the entire environment, the superposition appears to have vanished. The quantum interference effects that would reveal the superposition have leaked into the environment and become undetectable. The photon behaves as if it took one definite path, even though the full wave function of the universe still contains both possibilities. This process is extremely fast for macroscopic objects. Zurek calculated that a dust grain in the interstellar vacuum loses its quantum coherence in about 1/10,000th of a second. For an object at room temperature, the decoherence time is unimaginably short, less than 10 to the minus 40 seconds. Schrödinger's cat never experiences being in a superposition of alive and dead because the cat is constantly interacting with countless molecules of air, photons of light, thermal vibrations. The superposition decoheres almost instantaneously. Decoherence explains why we never observe quantum weirdness at everyday scales. It explains why measurements appear to have definite outcomes. It explains the emergence of the classical world from quantum foundations. But decoherence does not, by itself, solve the measurement problem. Because decoherence does not explain why we see one outcome rather than another. It does not explain where the other possibilities go. It just spreads them out into the environment, where they become undetectable but not non-existent. Decoherence is compatible with many worlds. It explains why the different branches do not interact. It is compatible with Copenhagen. It explains why measurements appear to give definite results, but it does not, on its own, tell us which interpretation is correct. The dark heart of the observer effect remains intact. In 1978, John Archibald Wheeler, the same physicist who had supervised Hugh Everett, proposed a thought experiment even stranger than Schrödinger's cat. Wheeler called it the delayed choice experiment. Here is the setup. A photon is fired toward a barrier with two slits. After passing the barrier, the photon travels toward a detection screen. So far, this is the ordinary double-slit experiment. But Wheeler added a twist. The choice of whether to observe which slit the photon went through is made after the photon has already passed through the slits. Think about what this means. If the decision to observe comes after the photon has committed to its path, then either the photon somehow knew in advance whether it would be observed, or the decision retroactively changes what the photon did in the past. Neither option makes sense according to our ordinary understanding of cause and effect. Wheeler went further. He imagined the experiment on a cosmic scale. Suppose light from a distant quasar is gravitationally lensed by a galaxy between the quasar and Earth. The light can take two different paths around the galaxy, each path billions of light years long. If we set up an experiment on Earth to detect which path the photon took, we observe particle behavior, no interference. If we set up an experiment to observe interference, we observe wave behavior. But the choice of experiment is made now, on Earth. The photon began its journey billions of years ago. Our choice today appears to influence what the photon was doing when Earth did not even exist yet. This is not science fiction. In 2007, Alain Aspect and his colleagues at the Institut d'Optique in France performed Wheeler's delayed choice experiment with single photons. In 2015, researchers at the Australian National University extended it to massive particles, helium atoms. The results confirmed quantum mechanics. The delayed choice affects the outcome exactly as predicted. The particle shows wave behavior or particle behavior depending on a choice made after the particle has passed the slits. There is no faster-than-light communication. There is no violation of causality in a strict sense. But there is something deeply unsettling about a universe where a decision made today can affect, in some meaningful sense, what happened before the decision was made. Wheeler drew a provocative conclusion from his thought experiment. He suggested that the past has no meaning until it is recorded in the present. No elementary phenomenon is a phenomenon until it is a registered phenomenon, he wrote. It is wrong to think of that past as already existing in all detail. The past is theory. The past has no existence except as it is recorded in the present. In 1982, Alain Aspect performed an experiment that would eventually earn him a share of the Nobel Prize in Physics, along with John Clauser and Anton Zeilinger. The experiment tested a prediction first made in 1964 by John Stuart Bell, a physicist working at CERN. Bell had analyzed the Einstein-Podolsky-Rosen thought experiment, the same paper that had prompted Schrödinger to devise his cat, and derived a mathematical inequality that set limits on what any local realistic theory could predict. Local realism is the combination of two intuitive ideas. Locality means that what happens here cannot instantaneously affect what happens over there. Influences propagate at most at the speed of light. Realism means that physical properties exist independently of whether they are measured. Einstein believed both of these ideas were fundamental to physics. He thought quantum mechanics, with its apparent dependence on observation, must be incomplete. There must be hidden variables, he argued, that determine the outcomes of measurements in advance. Quantum mechanics just does not have access to these hidden variables, which is why it can only predict probabilities. Bell showed that if local realism is true, the correlations between measurements on entangled particles must obey certain limits. He derived an inequality, now called Bell's inequality, that any local realistic theory must satisfy. Quantum mechanics, on the other hand, predicts that certain experiments will violate Bell's inequality. The correlations will be stronger than local realism allows. Aspect's experiment tested this prediction using pairs of entangled photons. The photons were sent to separate detectors, and the settings of the detectors were changed randomly while the photons were in flight, fast enough that no signal traveling at the speed of light could carry information between the detectors. The results violated Bell's inequality exactly as quantum mechanics predicted. Local realism is wrong. Either locality is wrong, meaning that influences can propagate instantaneously across arbitrary distances, or realism is wrong, meaning that particles do not have definite properties until they are measured, or both. This was not a blow to a fringe idea. This was experimental confirmation that our deepest intuitions about reality are simply incorrect. When Aspect's results were announced, the physics community took notice. John Bell himself called the experiment beautiful, but many physicists were slow to accept the implications. The work on quantum foundations, long considered a philosophical backwater, suddenly seemed urgent. In 2022, Aspect, Clauser, and Zeilinger were awarded the Nobel Prize in Physics for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. There is one more experiment we need to consider, one that takes the strangeness of the observer effect and pushes it to an almost unbearable extreme. It is called the quantum Zeno effect. The name comes from Zeno of Elea, an ancient Greek philosopher famous for his paradoxes. One of these paradoxes concerns an arrow in flight. At any given instant, Zeno argued, the arrow is not moving. It is simply at a location. If it is not moving at any instant, how can it move at all? The paradox is resolved by calculus. Motion is the limit of positions over infinitesimal intervals of time. But in quantum mechanics, Zeno's paradox takes on a strange new life. In 1977, E.C. George Sudarshan and Baidyanath Misra at the University of Texas proposed that repeated measurements could freeze a quantum system in place. If you observe a system frequently enough, they argued, it will never evolve. The wave function will keep collapsing back to its original state before it has time to change. A watched pot really does not boil if you watch it closely enough. This seemed like an outlandish prediction. But in 1990, Wayne Itano and colleagues at the National Institute of Standards and Technology tested it using beryllium ions. They found that rapid, repeated measurements dramatically slowed the transition of the ions from one energy state to another. With enough measurements, they could almost completely suppress the transition. In 2015, a team at Cornell University, led by Mukund Vengalatori, demonstrated the effect even more dramatically. They cooled a gas of rubidium atoms to near absolute zero and observed them constantly with a laser. The atoms, which normally would tunnel from place to place, a purely quantum effect, stopped moving entirely while being watched. In the quantum world, Vengalatori said, the folk wisdom really is true. A watched pot never boils. Think about what this means. By the act of observation, by simply looking, you can prevent a physical process from occurring, not by interfering with it, not by blocking it, just by observing it. This is the observer effect in its purest, most disturbing form. Reality, at its most fundamental level, is contingent on attention. Now we arrive at the dark side that nobody wants to admit. Throughout this discussion, we have danced around a question that sits at the center of the observer effect, like a black hole. What is observation, really? In the Copenhagen interpretation, observation collapses the wave function, but the interpretation does not specify what counts as an observation. A particle detector, a camera, a human eye, a conscious mind. In the many worlds interpretation, observation does not collapse anything. It just splits the universe. But the mathematics still does not explain why we experience one branch rather than another. Why does it feel like something to be an observer in one branch but not in all branches simultaneously? In Decoherence, observation is just a special case of environmental interaction. But decoherence does not solve the measurement problem. It just spreads the superposition out into the environment. The question of why we see definite outcomes remains. In objective collapse theories, observation is irrelevant. Collapse happens spontaneously. But these theories make different predictions from standard quantum mechanics, and those predictions have not been confirmed. Every interpretation of quantum mechanics struggles with the same fundamental issue. The role of the observer is either central but mysterious, or eliminated but at enormous cost. And here is what nobody wants to say out loud. We do not know what observation is. We do not know what makes a measurement a measurement. We do not know why the universe appears to care whether we are looking. For more than a century, physicists have used quantum mechanics to make predictions of extraordinary precision. The theory has been tested and confirmed in countless experiments. It underlies the technology of modern civilization: computers, lasers, MRI machines, atomic clocks. But the foundational question, what is the theory actually telling us about the nature of reality, remains unanswered. There is a philosophy called instrumentalism that says we should not worry about what our theories mean. A theory is just a tool for making predictions. As long as the predictions are accurate, the theory is successful. Asking what the theory really says about reality is a mistake. Many physicists adopt this view, at least implicitly. The famous phrase, "shut up and calculate," often attributed to Richard Feynman, but actually coined by N. David Mermin, captures this attitude. The math works. Do the math. Stop asking uncomfortable questions. But instrumentalism has a price. It means accepting that the most successful physical theory in history, the theory that describes atoms and light and all the forces of nature except gravity, tells us nothing about what the universe is actually like. It means treating physics not as a quest to understand reality, but as a mere catalogue of recipes for prediction. Some physicists are willing to pay this price, others are not. The struggle to understand the observer effect is, at its core, a struggle over the purpose of physics itself. Is physics about describing how things appear when we measure them? Or is physics about describing how things are, independent of our measurements? If the former, then the observer effect is just a feature of our interaction with the world, strange, but ultimately unimportant. If the latter, then the observer effect is a profound mystery that points to something we do not yet understand about the relationship between mind and matter. Some physicists have begun to take the second option seriously. In recent years, there has been a resurgence of interest in interpretations of quantum mechanics that place consciousness or information at the center of physics. Carlo Rovelli, the Italian physicist known for his work on loop quantum gravity, has developed an interpretation called relational quantum mechanics. In this view, the properties of quantum systems are not intrinsic but relational. They exist only relative to other systems. There is no view from nowhere, no absolute state of the universe. Every description is from a particular perspective. This is reminiscent of Einstein's insight in relativity. There is no absolute time, no absolute space, only time and space relative to an observer. Rovelli extends this to all of quantum mechanics. The wave function does not describe the absolute state of a system. It describes what one system knows about another. Others have gone further. Henry Stapp, a physicist at Lawrence Berkeley National Laboratory, has spent decades developing von Neumann and Wigner's ideas into a coherent framework that incorporates consciousness. For Stapp, quantum mechanics is not just about particles and fields. It is about the relationship between matter and mind. And in 2021, the philosopher David Chalmers and physicist Kelvin McQueen published a paper that took the consciousness causes collapse hypothesis seriously. They combined it with a mathematical theory of consciousness called integrated information theory, and showed that, under certain conditions, the hypothesis is not ruled out by experiment. These ideas remain controversial. Most physicists do not believe consciousness plays a special role in quantum mechanics. The mainstream view is that decoherence explains the appearance of collapse, and that the remaining interpretive questions are philosophical rather than physical. But the fact that serious physicists are revisiting these questions after decades of neglect suggests that the measurement problem is not going away. It is not a quirk to be explained away, but a clue to something deeper. And now we come to the darkest implication of all. Throughout human history, we have assumed that the universe exists independently of us. The stars would burn whether or not anyone was watching. The Earth would orbit the sun whether or not life evolved to observe it. Reality is out there, solid and complete, and we are just witnesses to it. Quantum mechanics challenges this assumption at its foundation. If the observer effect is real, if the act of measurement genuinely determines the outcomes of quantum events, then the universe is not independent of us. It is, in some sense, incomplete without observation. The wave function of the cosmos, if there is such a thing, requires observers to collapse it into definite reality. Wheeler, the great provocateur of physics, took this idea to its logical extreme. He proposed what he called the participatory universe, a cosmos in which observers are not passive spectators, but active participants in the creation of reality. We are participators in bringing into being not only the near and here, but the far away and long ago, Wheeler wrote. The universe does not exist out there, independent of us. We are inescapably involved in bringing about that which appears to be happening. This is not mysticism. This is the inference that some of the greatest physicists of the 20th century drew from the equations of quantum mechanics. And if they are right, then the dark side of the observer effect is not just that reality depends on observation. It is that we bear responsibility for the reality we observe. Every choice to measure or not measure, to look or not look, is a choice that shapes the universe. The moon does not exist, in Wheeler's view, until someone looks at it. Not because there is nothing there, but because the thing that is there is not definite until observation makes it so. Let us return to where we started. You have never touched anything in your entire life. The electrons in your fingertips and the electrons in everything you reach for hover apart, separated by quantum forces. But now, you know something more. The very notion of those electrons, the idea that they are there with definite positions and properties, depends on the act of observation. Before measurement, they are waves of probability, ghosts of possibility. After measurement, they are particles with specific locations, and you, the observer, are not outside this process. You are part of it. Your eyes absorb photons that have been bouncing off the world, interacting with quantum systems, carrying information that becomes definite only when it enters your consciousness. The boundary between you and the world is not sharp. It is quantum mechanical. It is smeared out across probabilities and possibilities. And the act of perceiving the world is not passive. It is creative. This is what the observer effect really tells us. It tells us that reality, at its deepest level, is participatory, that the universe is not a clockwork machine running according to predetermined rules, but a vast web of quantum possibilities that crystallize into actuality through the act of observation. It tells us that consciousness, whatever consciousness is not an epiphenomenon, a mere byproduct of material processes. It is, in some profound sense we do not yet understand, woven into the fabric of physics itself. It tells us that the question, what is real, has no answer independent of the question, who is looking? And it tells us that we are not witnesses to the universe. We are participants in its creation. There is one final thought experiment to consider. Imagine that you could view the universe from outside, from some God's eye perspective that sees all branches of the wave function, all possibilities at once. What would you see? You would see a vast tree of possibilities branching at every quantum event. You would see all the ways the universe could be, all simultaneously real. You would not see time flowing. Time, in this view, is an illusion created by the branching. The sense that we move from past to future is just the experience of moving along one branch of the tree. You would not see individual observers separate from the universe. Every observer is part of the tree. Their observations part of the branching structure. You would see that the question, what is real, is ill-formed. Everything is real, but no observer can see everything. Each observer, embedded in the tree, can only see the branch they are on. This is what quantum mechanics suggests, if we take it seriously and follow it to its conclusions. It is disturbing. It is counterintuitive. It violates our deepest assumptions about the nature of reality. But so did Copernicus, when he told us the Earth was not the center of the universe. So did Darwin, when he told us we are descended from apes. So did Einstein, when he told us that time is not absolute. Science has a history of humiliating our intuitions. Quantum mechanics may be the ultimate humiliation, the discovery that reality itself is not what we thought it was. So what do we do with this knowledge? We can, like many physicists, adopt instrumentalism. Shut up and calculate. Use the theory to make predictions. Do not worry about what it means. This is a defensible position, even a comfortable one. Or we can, like the philosophers and the seekers, keep asking the hard questions. Keep pushing on the foundations. keep demanding that physics tell us not just what will happen, but what is. This path is harder. It leads into paradox and confusion. It offers no easy answers. But it is the path that has always driven physics forward, the path of curiosity that will not rest until it understands. The observer effect has a dark side that nobody wants to admit. The dark side is that we do not understand it. After a century of quantum mechanics, after countless experiments and Nobel Prizes, we still do not know what observation is or why it matters. But there is light in this darkness too. Because the mystery remains, there is still something to discover. The foundations of physics are still unsettled. The great questions are still open. And somewhere, in the answers we have not yet found, lies a deeper understanding of reality than anything we have imagined. We are all observers. We are all participants. And the universe we observe, the reality we inhabit, is shaped by the very act of observation. That is the observer effect. That is its dark side. And that, perhaps, is its promise too. But we are not done yet, because there is another layer to this mystery, a layer that connects the observer effect to the very nature of knowledge itself. In 1927, the same year Heisenberg formulated the uncertainty principle, something remarkable happened in Brussels. 29 of the world's most distinguished physicists gathered at the 5th Solvay conference to discuss the newly emerging quantum theory. The photograph from that conference has become one of the most famous images in the history of science. In it, you can see Albert Einstein, Marie Curie, Max Planck, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and Wolfgang Pauli, among others. 17 of the 29 attendees were or would become Nobel Prize winners. But what happened at that conference was more than a meeting of great minds. It was a confrontation. Einstein could not accept what quantum mechanics seemed to be saying about reality. He believed in a world of definite objects with definite properties, a world where God does not play dice. At the conference, he challenged Bohr with one thought experiment after another, trying to show that quantum mechanics must be incomplete. Bohr defended the new theory. He and Einstein debated for days, walking through the conference halls, arguing over meals, scribbling diagrams on napkins. Each time Einstein proposed a contradiction, Bohr found a way to resolve it. Each time Einstein thought he had trapped quantum mechanics in an inconsistency, Bohr escaped. The debates continued for years, through subsequent Solvay conferences and in letters exchanged between the two men. Einstein never accepted quantum mechanics as a complete description of reality. He spent the last decades of his life searching for a deeper theory, one that would restore the classical determinism he believed in. He never found it. Today, most physicists believe Bohr won the debate. The experiments have consistently supported quantum mechanics and refuted the kind of hidden variable theories Einstein hoped for. But there is a sense in which Einstein's concerns have never been fully addressed. Einstein asked, "What is really happening when we are not looking?" Bohr's answer that the question is meaningless may be pragmatically sufficient, but it is philosophically unsatisfying. We still do not know what reality is like when no one is observing it. We may never know. The stakes of the Bohr-Einstein debate went beyond physics. They touched on fundamental questions about the nature of reality, the limits of knowledge, and the place of the observer in the universe. Einstein believed that physics should describe a world that exists independently of us. Bohr believed that physics could only describe our interactions with the world, that any attempt to go further was metaphysical speculation. This disagreement has never been resolved, and the observer effect sits at its heart. In 1927, Werner Heisenberg discovered something that would become known as the uncertainty principle. It is often misunderstood as a limitation of our measuring instruments, as if we just need better technology to measure things more precisely. That misunderstanding is profound, and it goes to the heart of what the observer effect really means. Heisenberg showed that certain pairs of physical properties are fundamentally incompatible: position and momentum, energy and time. You cannot know both members of these pairs with arbitrary precision. The more precisely you measure one, the less precisely you can know the other. This is not because your instruments disturb the system. It is built into the fabric of reality itself. The uncertainty principle can be written as an equation. The uncertainty in position times the uncertainty in momentum must always be greater than or equal to Planck's constant divided by 4 pi. This is not an approximation. It is an exact statement about the nature of reality. What does this tell us about observation? Consider trying to measure the position of an electron with perfect precision. To do this, you would need to use light with an extremely short wavelength. The shorter the wavelength, the more precisely you can locate something. But light carries momentum, and shorter wavelength light carries more momentum. When this high momentum light bounces off the electron, it transfers an unpredictable amount of momentum to the electron. You have measured the position precisely, but in doing so, you have made the momentum completely uncertain. Now consider measuring the momentum precisely. You need to use light with a very long wavelength, which carries less momentum and disturbs the electron less. But long wavelength light cannot pinpoint a precise location. You know the momentum, but now the position is uncertain. This seems like a practical limitation, but it is not. The uncertainty principle is not about disturbance. It is about the fact that position and momentum do not simultaneously exist as definite quantities. The electron does not have a precise position and a precise momentum that we fail to measure. It has one or the other, depending on how we observe it. The properties we observe are not pre-existing facts waiting to be discovered. They are created by the act of observation. This is what Bohr meant by complementarity. Wave and particle are not two sides of the same coin that we glimpse from different angles. They are two mutually exclusive realities that come into being depending on what we choose to look for. And this brings us back to the dark side. If the properties of quantum systems are created by observation, then what exists before observation? The Copenhagen answer is nothing definite. The many worlds answer is all possibilities. The objective collapse answer is a reality that becomes definite on its own terms, regardless of observation. None of these answers is comfortable. None of them matches our intuitive sense of a solid, pre-existing world that we merely perceive. There is something else we need to talk about. Something that emerges from the mathematics of quantum mechanics, but is rarely discussed outside of physics departments. It is called the no-cloning theorem. In 1982, William Wouters and Wojciech Zurek published a paper proving that it is impossible to make an exact copy of an unknown quantum state. This is not a technological limitation. It is a fundamental law of nature. If you have a quantum system in some state and you try to copy it, the best you can do is entangle the copy with the original in a way that does not give you two independent copies of the same state. Why does this matter for the observer effect? Because it means information about quantum states cannot be freely duplicated. If you want to know the state of a quantum system, you must disturb it. There is no way to measure a quantum state without changing it in some irreversible way. This is related to the uncertainty principle, but it goes deeper. The no-cloning theorem tells us that quantum information is fundamentally different from classical information. Classical information can be copied infinitely. You can make as many copies of a book or a computer file as you want. Quantum information cannot. This places a profound limit on what can be known about the quantum world. You cannot gather information about a quantum system without affecting it. Observation is not passive. It is active. It is creative. And it is irreversible. The observer does not just see the quantum world. The observer changes it. The no-cloning theorem has practical implications that extend far beyond philosophy. It is the foundation of quantum cryptography, a method of secure communication that is provably unbreakable, not by clever engineering, but by the laws of physics themselves. Here is how it works. Suppose you want to send a secret message to someone. In classical cryptography, you encode the message with a key, and anyone who has the key can decode it. The problem is that the key itself can be copied. If an eavesdropper intercepts the key, they can read your messages without you knowing. In quantum cryptography, the key is encoded in the quantum states of particles, typically the polarization of photons. Because of the no-cloning theorem, an eavesdropper cannot copy these states without disturbing them. If they try to intercept the key, they will inevitably introduce errors that you can detect. This means you can know with certainty whether your communication has been intercepted. And if it has not been intercepted, you can be certain that no one else has your key. Quantum cryptography is already in use today. Companies and governments use it to protect their most sensitive communications. The technology works precisely because the observer effect is real, because observation changes the system being observed. The dark side of the observer effect has a practical bright side, unbreakable security. But there is an even more remarkable application: quantum computing. A classical computer stores information in bits, zeros and ones. Each bit is definitely 0 or definitely 1 at any given moment. A quantum computer stores information in qubits, which can exist in superpositions of 0 and 1 simultaneously. This superposition is what gives quantum computers their power. A classical computer with 100 bits can be in one of 2 to the power of 100 possible states at any time. A quantum computer with 100 qubits can be in all of those states simultaneously, exploring every possibility at once. But there is a catch. The moment you observe a qubit, the superposition collapses. The qubit becomes a definite 0 or a definite 1, losing the quantum advantage. Quantum computation is a race against decoherence. The quantum information must be processed before the environment can observe it, before the superposition leaks away into the surrounding world. Building a quantum computer means creating a system that is isolated enough to preserve quantum coherence, but connected enough to allow controlled operations. This is extraordinarily difficult. Quantum computers must operate at temperatures colder than outer space, shielded from every possible disturbance. Even a single stray photon can destroy the delicate superpositions. And yet, quantum computers are being built. Companies like Google, IBM, and startups around the world are racing to create machines that can perform computations impossible for any classical computer. In 2019, Google announced that their quantum processor had achieved quantum supremacy, completing a calculation in minutes that would take the world's fastest supercomputer 10,000 years. The observer effect is not just a philosophical puzzle, it is a practical constraint that engineers must work around every day. The dark side of quantum mechanics is also the frontier of technology. Let us talk about decoherence more carefully, because it is the closest thing we have to a consensus explanation for why the classical world looks classical. Wojciech Zurek, the physicist at Los Alamos, who developed much of the theory of decoherence, has a vivid way of describing what happens. Imagine a quantum superposition, say an electron in a superposition of being here and being there. Now imagine this electron interacts with a single photon from the surrounding environment. The photon bounces off the electron and carries away information about where the electron was. That information is now encoded in the photon, which flies off into the environment. The electron and the photon are now entangled. The superposition has not collapsed, but it has spread out. The quantum coherence, the interference between the here and there states, is now shared between the electron and the photon. Now imagine this happens again and again. Every photon that scatters off the electron carries away more information. Every air molecule that bumps into the electron becomes entangled with it. The quantum coherence spreads further and further into the environment. From the perspective of an observer who only has access to the electron, the superposition appears to have vanished. The interference terms that would reveal the superposition have leaked away into the environment, where they are utterly inaccessible. The electron now appears to be either here or there, with classical probabilities. Zurek calls this process einselection, environment-induced superselection. The environment acts as a kind of continuous observer, monitoring the quantum system and selecting certain states as stable. These stable states are called pointer states, named after the pointer on a measuring instrument, which always points to a definite value. Pointer states are the states that can survive the constant monitoring by the environment. Other states, which would show quantum coherence, are rapidly destroyed. This explains why everyday objects do not appear to be in superpositions. A cat is constantly interacting with trillions upon trillions of air molecules and photons. Any superposition of alive and dead would decohere in an unimaginably small fraction of a second. By the time you open the box, the cat has been effectively measured by its environment countless times. But here is the catch. Decoherence does not explain why you see a particular outcome. The wave function after decoherence still contains both possibilities. The alive branch and the dead branch are both there. They just cannot interfere with each other anymore. The question of why you find yourself in one branch rather than the other, the question of where the other branch goes, remains unanswered. Decoherence plus many worlds says, both branches exist, and different versions of you experience them. Decoherence plus Copenhagen says, one branch is selected as real by some process that remains unexplained. Decoherence plus objective collapse says, one branch becomes real through a physical process that collapses the wave function. Decoherence tells us why we do not see quantum weirdness at everyday scales. It does not tell us what quantum mechanics says about reality. Zurich has gone further than decoherence. In recent years, he has developed an idea called quantum Darwinism. The basic insight is this: when a quantum system interacts with its environment, it does not just lose coherence, it also imprints multiple copies of its classical properties onto the environment. The environment becomes a kind of witness, carrying redundant records of what the system is doing. Think about how you perceive the world. You never observe quantum systems directly. You observe them through photons that have bounced off them, through vibrations that have propagated from them, through countless intermediaries that carry information about them. In quantum Darwinism, the information that survives this process, the information that gets amplified and distributed throughout the environment, is precisely the classical information about pointer states. The quantum coherences are lost, but the classical correlations are preserved and multiplied. This is why we perceive a classical world. The environment is constantly selecting classical properties and broadcasting them far and wide. The pointer states are the ones that can replicate their information most effectively. They are the fittest states in a Darwinian sense, the ones that survive and proliferate. Zurich's quantum Darwinism offers a picture of how objectivity emerges from the quantum world. Different observers accessing different parts of the environment can all agree on what they see because they are all accessing the same redundant records. The classical world is not an illusion. It is the information that has been selected and amplified by the environment. But again, this does not solve the measurement problem in its full generality. It explains why we agree on what we see. It does not explain why we see what we see rather than something else. There is a remarkable experiment that illustrates the subtlety of the observer effect more clearly than any other. It is called the quantum eraser. The basic setup is this: particles are sent through a double slit, and detectors are placed at the slits to record which path each particle takes. As expected, the interference pattern disappears. The particles behave like particles, not waves. But then comes the twist. The which path information recorded by the detectors is erased before anyone can look at it. And when the which path information is erased, the interference pattern returns. Let that sink in. The particles already went through the slits. The detectors already recorded which slit each particle went through. But that information was never observed by anyone, and when it is erased, the experiment behaves as if the measurement never happened. This seems to violate causality. How can erasing information after the fact change what the particles did earlier? The answer is subtle and depends on the details of the experiment. In most versions, the erasure involves correlating the particles with other particles in a way that makes the which path information inaccessible. But the original particles themselves do not change their behavior after the fact. The appearance of changing the past is an illusion created by how we analyze the data, but the philosophical implications are profound nonetheless. What matters for the interference pattern is not whether which path information exists, but whether which path information is accessible to us. The universe seems to care about what we can know, not just about what has happened. In 1999, a team of physicists performed a delayed choice quantum eraser experiment. They created entangled pairs of photons and sent one member of each pair through a double slit. The other member was sent to a series of detectors that could either preserve or erase the which path information. The key insight was that the choice to preserve or erase could be made after the first photon had already hit its detector. And yet, when the experimenters looked at the data, they found that the choice affected whether an interference pattern appeared. Again, this does not violate causality in a direct way. You cannot use this effect to send messages into the past, but it does suggest something strange about the nature of time and measurement. The past, as Wheeler said, has no meaning until it is recorded in the present. Let us pause to consider what all of this means for how we should think about science itself. Science has always been understood as a process of discovering facts about an objective world. The world exists out there with definite properties, and science is the method by which we learn what those properties are. The observer, the scientist, is supposed to be a passive recorder, not an active participant. Quantum mechanics challenges this picture fundamentally. If the observer effect is real, then science is not just about discovering facts. It is about creating them. The act of measurement brings certain properties into existence. The questions we choose to ask determine, in part, the answers we get. This does not mean that science is arbitrary or that anything goes. The mathematical structure of quantum mechanics places strict constraints on the what is possible. The probabilities are fixed by the laws of physics, not by the whims of observers. But it does mean that the relationship between subject and object, between the knower and the known, is more intimate than we thought. The observer is not separate from the universe being observed. The observer is part of it. This has implications for how we think about objectivity. In classical physics, objectivity meant describing the world as it is, independent of any observer. In quantum physics, this kind of observer-independent objectivity may not be achievable. The best we can do is intersubjective agreement, a consensus among observers who are all part of the same quantum system. Some philosophers see this as a vindication of certain ideas in Eastern philosophy. The notion that the division between self and world is an illusion, that observer and observed are aspects of a single underlying reality. Whether such connections are profound or superficial is a matter of ongoing debate. What is clear is that quantum mechanics forces us to reconsider assumptions that have been foundational to Western thought since the ancient Greeks. The idea of an objective world existing independently of minds perceiving it. This idea, which seems so obvious and necessary, may not survive the quantum revolution intact. There is a thought experiment that brings the strangeness of the observer effect into sharp focus. It was proposed by Wigner, but it has been refined and developed by many physicists since. The experiment is a variation on Schrödinger's cat, but instead of a cat, it involves a conscious human being, Wigner's friend. Imagine Wigner is outside a sealed laboratory. Inside the laboratory, his friend performs a quantum measurement, say, measuring the spin of an electron. The electron can be spin up or spin down, with equal probability. From the friend's perspective, the measurement has a definite outcome. The friend sees either spin up or spin down and knows which one it is. The wave function has collapsed and the electron has a definite state. But from Wigner's perspective outside the lab, the situation is different. According to quantum mechanics, the friend, the electron, and the measurement apparatus are all part of a single quantum system. Until Wigner opens the door and looks inside, this system exists in a superposition. From Wigner's perspective, the friend is in a superposition of having seen spin up and having seen spin down. The friend's brain, the friend's experience, the friend's memory. All of these are indefinite until Wigner observes them. But wait, the friend does not experience being in a superposition. The friend experiences a definite outcome. How can both perspectives be correct? This is where the interpretations diverge most dramatically. In the Copenhagen interpretation, there is no clear answer. Bohr would say that we cannot meaningfully describe what happens inside the lab until Wigner opens the door. The question of what the friend experiences before Wigner observes is not a scientific question. In many worlds, there is no paradox. When the friend makes the measurement, the universe branches. In one branch, the friend sees spin up. In another branch, the friend sees spin down. Both branches are equally real. When Wigner opens the door, he becomes entangled with the friend, and further branching occurs. Every possible combination of experiences is realized somewhere. In objective collapse theories, the friend's measurement triggers a collapse long before Wigner gets involved. The superposition does not persist for macroscopic systems like human brains. The friend has a definite experience, and Wigner will discover what it was when he opens the door. In recent years, physicists have begun to perform actual experiments inspired by Wigner's friend. Not with conscious observers, of course, but with quantum systems that play the role of observers. These experiments probe the limits of how far superposition can extend and whether there is any point at which collapse must occur. The results so far are consistent with quantum mechanics, extending all the way up. There is no sign of a fundamental limit on superposition. If such a limit exists, it lies beyond what we can currently test. Now we need to confront the hardest question of all. What is consciousness? And does it have anything to do with quantum mechanics? We have seen that some interpretations, von Neumann's, Wigner's early work, suggest that consciousness plays a special role in collapsing the wave function. Most physicists reject this view today, but rejecting it does not make the question go away. Here is the puzzle. Quantum mechanics describes a universe of probabilities, superpositions, and entanglements. It describes a universe where particles do not have definite properties until they are measured. It describes a universe where the act of observation plays a central role in the dynamics, and yet we experience a world of definite objects, stable properties, and clear perceptions. We experience a world where cats are alive or dead, not both. We experience a world where we observe things, but do not change them by observing. How does the classical world emerge from the quantum substrate? How does our experience of a stable, definite reality arise from a universe that, at its foundation, is neither stable nor definite? Decoherence provides part of the answer. The environment monitors quantum systems so rapidly that superpositions never persist long enough to be observable. But decoherence does not explain why we experience one outcome rather than all outcomes. Many worlds provides another answer. We experience one outcome because we exist in one branch of the universal wave function. But this raises its own puzzles. Why does it feel like something to be in one branch? Why does consciousness seem to pick out a single thread of experience from the vast tapestry of all possibilities? And here is where the hardest question meets the darkest implication. We do not have a good theory of consciousness. We do not know what consciousness is, how it arises from physical processes, or why there is something it is like to be a conscious being. This is called the hard problem of consciousness, and it remains one of the deepest unsolved problems in philosophy and science. Until we understand consciousness, we cannot fully resolve the measurement problem, because the measurement problem, at its core, is about the relationship between the objective quantum world and the subjective experience of observation. Some physicists believe the two problems are connected. They believe that a true understanding of quantum mechanics will require a true understanding of consciousness, and vice versa. Others believe the problems are separate, that consciousness is a high-level emergent phenomenon that has nothing to do with quantum effects. We do not know who is right. The connection between consciousness and quantum mechanics has attracted not just physicists, but also charlatans. The observer effect has been invoked to justify all manner of pseudoscience and mysticism. From the claim that you can manifest your desires by observing them into existence, to the idea that quantum mechanics proves the existence of God. These claims are almost always based on misunderstandings. The observer effect does not mean that consciousness creates reality in any naive sense. It does not mean that you can change the world by thinking hard enough. It does not mean that quantum mechanics validates New Age beliefs. The observer effect is about the interaction between quantum systems and measuring devices. It is about the strange correlations that arise when information is extracted from quantum states. It is subtle, technical, and constrained by precise mathematical laws. And yet, the temptation to read deeper meanings into it is understandable. Quantum mechanics does seem to say something profound about the relationship between mind and matter. It does challenge our ordinary understanding of objectivity and reality. It is not surprising that people grasp for interpretations that resonate with their existing beliefs. The challenge for scientists and educators is to convey the genuine strangeness of quantum mechanics without feeding into pseudoscience. This is harder than it sounds. The truth about the observer effect is strange enough. You do not need to exaggerate it to make it interesting. Consider what we actually know. We know that quantum systems behave differently when measured than when unmeasured. We know that the act of extracting information from a quantum system disturbs the system in irreducible ways. We know that the properties of quantum systems seem to be defined only relative to specific measurements. These facts are strange and profound, but they do not tell us that consciousness creates reality or that intention shapes the physical world. They tell us something much more subtle, that the relationship between observer and observed is not the simple one we imagined in classical physics. Being precise about what quantum mechanics does and does not say is essential. Otherwise, we lose the ability to distinguish genuine scientific mystery from wishful thinking dressed up in scientific language. There is one more angle from which we should approach the observer effect. It has to do with time. In classical physics, time is straightforward. The past determines the future. Causes precede effects. The arrow of time points in one direction, from order to disorder, from past to future. Quantum mechanics complicates this picture. Consider the delayed choice experiments we discussed earlier. The choice of how to measure a particle, made after the particle has already traveled through the slits, seems to affect whether the particle behaved as a wave or a particle during its journey. Or consider entanglement. When two particles are entangled, a measurement on one particle instantaneously affects what will be found when the other particle is measured, no matter how far apart they are. This does not allow faster than light communication, but it does suggest that the correlations in nature are not bound by our ordinary sense of cause and effect. Some physicists have proposed that the apparent arrow of time is itself a consequence of the observer effect. When we make observations, we create records, memories, photographs, data files. These records distinguish the past from the future. Without observers to make records, there would be no distinction. In this view, time as we experience it is a feature of observation, not of fundamental physics. The equations of quantum mechanics are symmetric in time. They work equally well, run forward or backward. The apparent direction of time emerges from the thermodynamic processes that allow records to form. This is speculative, but it points to another way in which the observer effect touches on the deepest questions. Our experience of time, our sense that moments pass and change accumulates, may itself depend on the fact that we are observers creating records. Without observers, would time exist at all? There is one more idea we should explore, an idea that might seem like science fiction, but is taken seriously by some physicists. What if the universe is fundamentally made of information? This view has been advocated by John Wheeler, who coined the phrase "it from bit." The idea is that physical reality is not primary. Information is primary. The universe is, at its foundation, a vast computation or a vast information structure. In this view, the observer effect is not mysterious at all. If the universe is information, then observation is just the process by which information becomes definite. The wave function is information about what might happen. Measurement is the process by which this information becomes information about what did happen. Wheeler imagined a participatory universe in which observers play an essential role in bringing information into existence. The universe is not a machine that runs on its own. It is a participatory process in which minds and matter are inextricably intertwined. This is speculative. There is no experimental evidence that forces us to adopt this view, but it has a certain elegance. It explains why observation matters, because observation is the process by which information becomes real. It explains why the universe seems to care about what we can know, because knowledge and reality are not separate things, and it suggests a profound answer to the question of why there is something rather than nothing. If the universe is information, then existence is not a mysterious given. Existence is what happens when information becomes self-consistent, when the vast network of observations and observations of observations ties together into a coherent whole. We are not observers of the universe. We are the universe observing itself. Let us step back and take stock of where we are. We began with a simple experiment: light passing through two slits. We discovered that this simple experiment reveals something deeply disturbing about the nature of reality. Quantum systems do not have definite properties until they are observed. The act of observation changes what the system does. The observer is not a passive witness, but an active participant in the creation of reality. We explored the various interpretations of quantum mechanics: Copenhagen, many worlds, objective collapse, decoherence, and found that none of them fully resolves the mystery. Each one either leaves observation unexplained or introduces enormous metaphysical baggage. We looked at experiments that push the observer effect to its limits. The delayed choice experiment, which seems to allow the present to influence the past. The quantum Zeno effect, which shows that observation can freeze systems in place. The quantum eraser, which shows that erasing information can change experimental outcomes. We confronted the question of consciousness and found that we cannot fully understand the observer effect until we understand what consciousness is, a problem that remains unsolved. And we considered the possibility that the universe is fundamentally made of information, and that observation is the process by which information becomes real. Throughout all of this, one theme has emerged again and again. The observer effect tells us that the boundary between mind and matter is not as sharp as we thought. The objective world out there and the subjective experience in here are connected in ways that physics has not yet explained. This is the dark side of the observer effect. It is not just that quantum mechanics is strange. It is that quantum mechanics challenges our most basic assumptions about the relationship between ourselves and the world. Let us spend a moment considering what it would mean if we could actually resolve the measurement problem. What would change if we found that consciousness truly does collapse the wave function? If the von Neumann-Wigner hypothesis were confirmed, it would be the most revolutionary discovery in the history of science. It would mean that physics, at its foundation, involves something non-physical. It would overturn materialist philosophy. It would transform how we think about death, identity, and the relationship between mind and body. But the experimental evidence for this is weak. Most physicists believe consciousness is not special, that any measuring device, conscious or not, triggers the appearance of collapse. The challenge is explaining why. If we found that the many worlds interpretation is correct, if all branches of the wave function are equally real, that would also be revolutionary. It would mean that you are not unique. There are versions of you in other branches, living different lives. Some are happier than you. Some are suffering more. Some made different choices and became different people. This has strange implications for ethics and decision-making. If every choice leads to a branch where you made the other choice, what does it mean to choose? Some philosophers have argued that many worlds undermines free will. Others argue it makes free will more mysterious, not less. If we found that objective collapse theories are correct, that there is a physical process causing wave function collapse, we would have discovered new physics. The Schrödinger equation would be modified. New phenomena would become predictable, and we would understand, finally, where the quantum world ends and the classical world begins. Each resolution would be momentous. each would reshape physics and philosophy. And yet, a century in, we have not been able to distinguish between them experimentally. This might be because the differences are too small to measure with current technology. Or it might be because the interpretations are all saying the same thing in different languages, that there is no fact of the matter about which is correct. Or it might be that we are missing something fundamental, that the true resolution of the measurement problem requires ideas we have not yet conceived. Here is one such idea, which has gained traction in recent years. Perhaps the measurement problem dissolves if we stop thinking of the wave function as describing an individual system and start thinking of it as describing the relationship between systems. This is the core insight of relational quantum mechanics, proposed by Carlo Rovelli in 1996. In this view, the properties of quantum systems are not intrinsic to the systems themselves. They are defined only relative to other systems. When you measure the spin of an electron, you do not discover a property the electron had all along. You establish a relation between yourself and the electron. Another observer, measuring from a different perspective, might establish a different relation. There is no absolute fact about what the electron's spin is. There are only relational facts, facts relative to particular observers or systems. This sounds relativistic in a philosophical sense, and Rovelli explicitly draws the analogy to Einstein's relativity. Just as there is no absolute simultaneity in special relativity, events that are simultaneous for one observer are not simultaneous for another. There are no absolute properties in relational quantum mechanics. If this view is correct, the observer effect is not mysterious. It is just what it means for properties to be relational. Observation does not collapse the wave function or create reality in any special sense. Observation establishes a relation between observer and observed. That relation is what we call a measurement outcome. Relational quantum mechanics has its critics. Some argue that it does not really solve the problem, but just restates it in different terms. Others argue that it makes physics too subjective, undermining the intersubjective agreement that allows science to function. But it represents one way of dissolving the measurement problem, without invoking consciousness, without multiplying universes, and without modifying the Schrödinger equation. It is a reminder that the interpretive space of quantum mechanics is vast, and we may not have explored all of it yet. Let us also consider what the observer effect tells us about the limits of scientific explanation. Science explains phenomena by reducing them to simpler, more fundamental constituents and laws. We explain the behavior of gases by appealing to the motions of molecules. We explain the behavior of molecules by appealing to the bonds between atoms. We explain the behavior of atoms by appealing to the interactions of protons, neutrons, and electrons. But what happens when we reach the bottom? What explains the fundamental laws themselves? In classical physics, we could at least imagine a mechanical universe, particles bouncing around according to fixed rules, with no need for explanation beyond the rules themselves. The universe was a machine. It just ran. Quantum mechanics does not offer this comfort. The fundamental laws involve probabilities, superpositions, and the undefined status of properties before measurement. They invoke observation without defining it. They describe a reality that is not fully real until it is perceived. Perhaps this is a sign that we have reached the limits of mechanical explanation. Perhaps at the deepest level, the universe is not a machine at all. Perhaps it is something more like a network of observations, a web of relations, a process of becoming rather than a collection of things. This is philosophically dizzying. It challenges the assumption, implicit in physics since Newton, that reality is fundamentally mechanical. But quantum mechanics has always challenged our assumptions. There is no reason to expect the final theory of physics to be comprehensible in terms derived from everyday experience. The night sky is full of stars. Each star is a sun, burning through nuclear fusion, converting hydrogen into helium, releasing energy that travels across light years to reach your eyes. When a photon from a distant star enters your eye, it has been traveling for millions of years. All that time, it was a wave of probability, spreading out through space, undefined in position. Only when it strikes your retina does it become definite. Only in the moment of observation does it become a fact. In some sense, you have just participated in bringing that photon into existence. Your observation created a connection between here and there, between now and millions of years ago. You have reached across space and time and made something real. This is not poetry. This is what the physics says. When you look at the night sky, you are not passively receiving information about a distant universe. You are actively participating in the universe's self-observation. You are part of the process by which the quantum potential becomes classical fact. There is something profound in this, something that connects the largest and smallest scales of existence. The stars exist because observers like us, made of stardust, look back at them. The universe knows itself through us. This is not anthropocentrism. Other observers would work just as well. Aliens on distant worlds, or future artificial intelligences, or any system capable of making irreversible records. The point is not that humans are special. The point is that observation is special. It is the process through which the indeterminate becomes determinate. And we are part of that process, not by accident, but by necessity. There is a story about Niels Bohr, the great architect of quantum mechanics. A colleague once visited Bohr at his country house and noticed a horseshoe hanging above the door. "Surely you don't believe in that superstition?" the colleague said. Bohr replied, "Of course not, but I'm told it works whether you believe in it or not." Quantum mechanics is like that horseshoe. It works whether we believe in it or not. It makes predictions that are confirmed by experiment to extraordinary precision. It underlies all of modern technology. But we do not understand it. And here is the unsettling truth. We might never understand it. Not because we are not smart enough, but because understanding quantum mechanics might require changing what we mean by understanding. Our intuitions are built on the classical world. We evolved to deal with medium-sized objects moving at medium speeds, the world of rocks and trees and tigers. Our brains are optimized for that world. Our concepts of space, time, causality, and identity are adapted to that world. The quantum world is different. It operates according to rules that our evolved intuitions cannot grasp. When we try to form mental pictures of quantum mechanics, we fail, not because the math is wrong, but because the reality the math describes has no classical analog. Feynman understood this. That is why he said not to ask, "How can it be like that?" You will get nowhere. Nature is under no obligation to make sense to creatures who evolved on the African savanna. But we cannot help asking. That is what makes us human, the drive to understand, even when understanding seems impossible. So where does this leave us? We are observers in a universe that seems to require observers. We are conscious beings in a universe where consciousness might play a role in the fundamental physics. We are participants in a reality that is not complete without participation. The observer effect has a dark side. Yes, it undermines our naive confidence in an objective reality that exists independently of us. It raises questions we cannot answer. It suggests that the very fabric of the universe is woven through with the threads of observation and knowledge. But there is another way to look at this. If the observer effect is real, if observation truly matters, then we are not incidental to the universe. We are essential to it. Our consciousness, our perception, our knowledge are not epiphenomena sitting on top of a mechanical cosmos. They are part of the machinery itself. We matter, not in a sentimental sense, but in a physical sense. The universe would not be what it is without observers like us. This is not a proof of meaning or purpose. The universe does not care about our happiness or our suffering any more than it did before, but it suggests that consciousness, whatever consciousness turns out to be, is not a cosmic accident. It is a cosmic necessity, and that, perhaps, is the light on the other side of the darkness. The year 2025 marks 100 years since the formulation of modern quantum mechanics. A century ago, Heisenberg, Schrödinger, Dirac, and others wrote down the equations that would revolutionize physics. Those equations have been tested billions of times. They have never failed. And yet, after a century, we still do not know what they mean. The measurement problem is not solved. The interpretations of quantum mechanics remain multiple and incompatible. The relationship between observation and reality is as mysterious as ever. This is not a failure of physics. It is a marker of how deep the problem goes. Quantum mechanics works. It is the most successful theory in the history of science. But understanding it, really understanding it, has proved harder than anyone expected. Perhaps the next century will bring resolution. Perhaps some young physicist working in obscurity will have an insight that cuts through the confusion. Perhaps new experiments will rule out some interpretations and support others. Perhaps we will finally understand what observation is and why it matters. Or perhaps the mystery will persist. Perhaps the observer effect is not a problem to be solved, but a feature to be accepted. Perhaps the universe is just this strange, and our job is to make peace with it. Either way, the journey continues. The questions remain open. The darkness hides possibilities we have not imagined. You have never touched anything in your entire life. Now you know why. The electrons in your fingertips and the electrons in everything you reach for are quantum systems. They do not have definite positions until those positions are measured. The contact you feel is electromagnetic repulsion mediated by photons, experienced as sensation only when information about it enters your consciousness. You are separated from the world by a quantum gap, but you are connected to it by something deeper, by the process of observation through which world and mind define each other. This is the observer effect. This is its dark side, and this is its beauty. We are not merely observers of the universe. We are the universe's way of observing itself. And in that observation, reality is born. So where do we go from here? The observer effect has taken us on a journey through some of the strangest territory in science. We have encountered experiments that defy common sense, interpretations that multiply universes or erase the distinction between observer and observed, and questions that touch on the deepest mysteries of existence. But science is not just about contemplation. It is about progress. Right now, around the world, experiments are being designed to probe the foundations of quantum mechanics more deeply than ever before. Physicists are creating larger and larger quantum superpositions, testing the limits of coherence and looking for signs of objective collapse. They are building quantum computers that exploit the very features of quantum mechanics that make it so strange. They are sending entangled photons through Earth's atmosphere and into space, testing the universality of quantum correlations. Philosophy, too, is advancing. Scholars are refining the interpretations of quantum mechanics, working out their implications and debating their merits with new rigor. The old assumption that interpretation is just philosophy and irrelevant to real physics is giving way to a recognition that the foundational questions matter. And perhaps most importantly, a new generation is discovering quantum mechanics for the first time. Students around the world are encountering the double-slit experiment, grappling with the uncertainty principle, and asking the same questions that puzzled Einstein and Bohr. Among them, somewhere, may be the mind that finally cracks the puzzle. The observer effect has a dark side nobody wants to admit, but that darkness is also fertile ground. It is where new understanding grows. The photon passes through both slits. The wave function collapses, or does not. The cat waits in its box. The universe branches or remains whole. And somewhere, an observer watches, wondering what it all means. That observer is you. What will you discover?